Hello everybody, my name is Soto. I am a machine learning researcher at Brookhaven National Lab. My research there involves developments and uses of machine learning and natural language processing for a number of scientific and some security applications as well. A lot of my work recently has been in machine learning for nuclear non-proliferation. But today I'm going to be talking about a much more general application of machine learning, and one that I think might have a lot of applications in this room and many other rooms. So I'm going to be speaking about using machine learning to take information that is currently not machine readable and make it machine readable. And this is all about scale, about information at scale and being able to leverage that information at scale. I'm going to talk about some of the successes that I've already been seen in one particular area of scalable information extraction. And then I'm going to look at three specific problems: information in documents, information in tables, and information in charts. And I'm going to talk about, very briefly, a vision for what you can do with this. So when I talk about scale, the motivation for this work is looking at documents, but this is not really limited to documents. There's many missions and efforts out there in the world, and I'm sure in this room, that require analyzing enormous amounts of information, very vast and disparate information resources. And the problem is that a significant amount of that information is not machine readable. And it's a problem because these resources are going to be what you use to inform your next experiments. They're going to be the context that you use to help interpret your results. They're going to help you perform new large-scale analyses that you wouldn't be able to perform with much more limited sets of data. And the scale of these resources is really what limits their effectiveness. It inhibits the exploitation of their full potential. To look at one particular application and one that's been motivating for my own work, scientific literature. Publication rates have been growing exponentially. This here is a plot of the archive, a preprint server for physics, computer science, and many other disciplines. You see that every single one of these groups is growing exponentially. That means that anybody working on any particular problem who wants to inform their next experiments, who wants to inform their new research with the state-of-the-art in the literature, has more and more papers to look at every single year, and they're never ever going to be able to keep up. And of course, it's impossible to manually survey all the relevant works for any given problem. But let me talk about the problems that motivated my work. In biology, I'm working on problems of using natural language processing to help describe protein-protein interactions in literature, or describe genetic toolkits in literature. This is part of an effort for the BER, Biological and Environmental Research Program's K-base project. And that figure right there shows kind of some of the components of that work. In chemistry, I'm working on NLP for a similar problem, also in the literature, looking for research that can help parameterize new experiments for isotope separations. The isotope program at BNL is heavily involved in the development of actual products, isotopes that are delivered to hospitals and to organizations, including one that's a very keen interest, actinium-225. You see here the results of a very successful clinical trial usage of actinium-225 for prostate cancer. And the problem is, we know that the isotope is very promising for this kind of work, but it's very hard to make it at scale. We have less than 0.1% of the amount of this isotope that would be necessary to do clinical trials at scale and for production. And getting that isotope means irradiating a sample and then chemically separating the isotope that you want from that sample. But it normally takes a postdoc about a year to design the experiment to get that to work. So if we can inform that with some prior work, that would be very informative. And then nuclear physics, the NNDC at BNL, the National Nuclear Data Center, they kind of hold the authoritative data sets for a lot of nuclei information, half-lives and state changes that are used by the world, by the community, and they fill these data sets by reviewing the literature. They go and read 10,000 papers and look at all of the experiments that have experimentally derived these properties, these values, and then they use their domain expertise to evaluate these and enter the correct value to the database. All of these are highly manual processes. All of these are highly manual workflows. And that's something that's in common for many other problems as well. And so what I want to look at is how can we use machine learning to accelerate these highly manual workflows. Look for the part of that workflow that really can be filled in with some machine learning. And it's not just about accelerating current workflows, it's also about enabling new capabilities, especially observation of emergent patterns that you wouldn't see until you look at a lot of data at scale. For an obvious example, actinium-225 is an actinide. It and other actinides in that part of the periodic table are going to have similar chemical properties. And if you see chemical separation experiments that were done for this isotope and this isotope, but not for this one in this gap of the periodic table, you can infer a lot of the properties that would be relevant for your own experiments. And you really only see that when you have filled in a lot of this table. Now, you all know that natural language processing, large language models in particular, has been a very visible success story for information processing at scale. And specifically, knowledge retrieval has been a very talked about capability of these large language models. In fact, it's kicked off an entire new arms race for AI development, and everybody's throwing money at this. You might know that the background for this is fairly recent as well. The transformer architecture that enabled all of this scalability only came out in 2017. And the very first LLMs came out just a year later in 2018. But of course, it got public attention in 2022 with ChatGPT. Now, the reason this is important is because it's a good demonstration of why scale matters. These LLMs have been pre-trained on a very simple machine learning objective. It's language modeling, next token prediction, next word prediction, basically. But the reason they work is because we pre-trained them on enormous text corpora, billions of words. And the problem there is that you're limited to machine-readable text. All of the data that was used to pre-train these large language models was scraped from the web. It's still a very useful tool, but it kind of shows you some of the limitations of what it means to get machine-readable information into your models. Now, these models scale their performance. It scales as a power law, a power function of compute time, training data, and the size of the model, the number of parameters of the model. And those plots there show you those parameterizations. Those are log-log plots, by the way, so that straight line is a power function. And these scaling properties also hold for other modalities of data. This is for text data, but it also holds for other modalities. And these are generally called foundation models when we talk about non-text specific large models. In fact, it's a little more nuanced than that, but I have some issues with that terminology. Now, the properties that made these models work at scale come down to these three categories of scale, of compute time, training data, and parameterization of your models. The training data, for the purpose of this talk, is going to be the important one because the model's ability to kind of pseudo-memorize its training corpus is what has enabled all of these very impressive generative capabilities. But again, that data was all scraped from the web. This is web data, and other sources are not as easy to access. Now, I said that the majority of the work that I've been working on is about documents, so that it's not limited to documents. And even though it's increasingly common and popular to encourage or even mandate open publication of your data and machine-readable documents, so like make your new paper HTML so that it can be put on the web, or release the raw LaTeX or the raw Word documents. These standards are not really the norm yet, and the vast majority of publications, the vast majority of documents are not machine-readable, including very vast historical archives. These FAIR principles right here, by the way, are what I'm talking about when I say these new mandates for open publications. Scanned documents are the obvious problem. We can do OCR, that is optical character recognition, to enable like text search, which is very powerful and very enabling, but it doesn't really capture the organization of these documents. And it completely misses other contents in the documents. Tables are going to turn into like individual characters, and figures are just ignored altogether. But even born digital documents are still a problem. And you might think that if you take your Word document and save it as a PDF, now you have a machine-readable document. No, you do not. See, PDFs are encoded to be machine displayable, machine printable, not machine readable. They're consistent in how they're displayed, not consistent in how they're embedded. If you've ever tried to copy a page out of a PDF into Word, you will see some of the artifacts that emerge. If you've ever tried that with a table, you'd probably bang your head on a wall trying to fix that table in Excel. The problem is that naive PDF extraction tools are heuristic in nature. They scrape out the raw text, but every single character of that text is actually just encoded as pixel coordinates on a page. And a bunch of handcrafted rules are what are deciding how to piece all that back together into documents. They're not very robust. The ordering and structure is not guaranteed at all. And you're going to get a lot of artifacts, a lot of errors in your extractions. Headers and line numbers and captions are going to be all mixed together. And if you want to use this information as a canonical resource for information extraction, now you've introduced a lot of errors into your resource. And as I said already, tables are going to be a particular problem because of the structure, the necessary structure that the tables encode. And doing that parsing with heuristic rules is extremely noisy. And then figures and charts are just basically ignored. It's an altogether ignored problem. These extraction errors, as I already said, they really impair the scalability of information extraction. Now, what can we do about that? Well, these are some images of some scientific papers. And even though you cannot read that text, you can probably tell which of those color-coded regions are the titles, which are the authors, which is the abstract, where the figure caption is. That's because it's an easy visual task to accomplish. And so we can actually address this problem with some computer vision, machine learning for computer vision. And we can do much, much better in that domain than we could with the traditional and previous methods that do this information extraction, which are all based on the metadata and markup that encodes these documents. We can actually use object detection models for this task very successfully. The exact same models that you use to train object detection for a self-driving car and make sure it doesn't hit a pedestrian or a bicyclist, you're going to use those exact same models for this problem, except that your objects are now just regions in the page. And it's a very direct application and it works extremely well. Now there's some headroom and you can do improvements, and we showed those improvements if you exploit the properties of your structured documents, because you know where in the pages some of these contents are going to be, so you can exploit some of that information to get better performance. Our results show that we can get very high precision on the information extraction that we want to do. And of course, since it's a machine learning method that's very fast at inference time, it's extremely efficient, 14 times faster than previous methods. So, an obvious win. But the harder problems are the particular modalities that have been historically difficult to extract with traditional methods. Table extraction, as I already said. If you ever try to copy and paste a table out of a PDF and then insert it into Excel or Word or something, you're going to have a lot of errors. These are some of the kinds of errors that you'll see. You're going to have broken characters if your character set is not supported. You're going to have merged columns and cells completely out of place. And all of these are due to the nature in which the extraction methods are trying to extract and parse this information together, which is all heuristic based. It's all rule based, handcrafted rules. But we can do much better, as I already said, with machine learning. And for this work, we took two approaches. First, we started with a mixed image-text approach, where we tried to treat this as a similar problem to the previous object detection, and then you clean it up after the fact with some text processing. Because you can just encode this as a text stream, like a CSV file or HTML tags, once you have the extracted information, and then do a text-to-text translation to kind of clean up the structure errors. And that's what we did at first. We got really good performance on the detection parts of the problem. Make sure that you know where the bounds of the table are, make sure you know where the cells are located. You can see that the results are 98%, 99%, 96% F1. But the structure prediction, making sure that everything's in the right place, was still really hard, even after we tried to do a text-to-text correction model. Now, we did a much better job once we just gave up on the text part and treated it as an image problem. If you treat this as just an image problem, then you can just do a transformer-based object detection model, apply it directly to this task, and if you have enough training data, it works extremely well. And this might have been us throwing up our hands and giving up and saying that the gods of machine learning have got us again. More data, more model, more machine learning always is more better. And unfortunately, in this case, that was exactly the situation. This model was pre-trained on about 1 million machine-annotated tables, so not perfect annotations, and then fine-tuned a little bit on our particular data set. But by treating the structure prediction task, which was previously done in the text space, as a specialized version of an object detection task, and that's what that looks like in the top right, we kind of eliminated that whole structure prediction problem. That structure prediction jumped from 78.2 to 98.5 on this particular structure prediction metric. And that's kind of a lesson learned as far as the methods that you employ for your particular problem. Scale tends to win. And this is kind of the change that we had to make. All of those green blocks were the pipeline that we had developed over about a couple of years and had still struggled mightily with the structure creation task. And then once we had enough data and a large enough model, that orange block right there kind of just replaced all of those, and now it's kind of a solved problem. It's still a problem though if you cannot get structure resolving annotations in place to do the final tuning for your particular domain. But to some degree, you can address that with some domain annotation. So it's an approachable problem. Now, the hard one, reverse engineering data charts. How do you take that chart right there and turn it back into a table? You and I can look at that chart and say, okay, this bar is 18.5, and this bar is about 16.2 because I can look at the axes and estimate. You cannot do that for 10,000 charts. You cannot do that for 1,000,000 charts. And you certainly cannot hire enough people to do that either. So if we want to apply machine learning to this problem, we have to look at two problems. First, we have to recognize where all of these charts are, what type of chart they are, and then do the information extraction. Recognizing where the charts are, that's actually kind of easy. We can do that with the previous method, the document layout analysis, recognize where components of the document are. Or we can just throw a regular object detection model at this problem and get very good results anyway. If you just use an off-the-shelf YOLO v3 model for this problem, you can get 95% mean average precision, which is very good. So this part of the problem is not the hard part of the problem. What is a nuance of this part of the problem is that the bounding box for your chart is going to not be very perfect. It's going to sometimes chop into the chart, and sometimes it's going to exclude external artifacts into your chart. So necessarily, you have to oversample any detected charts and then rely on your extraction model to do a very good job at ignoring all of this spurious information. It must be robust to artifacts. And so we developed a model that does exactly that. It's a point proposal network. It's based to some degree on region proposal networks for object detection models. If you know it, faster RCNN is kind of where the inspiration came from. But instead of predicting regions of interest in an image, we recognize points, and the point is the data. So we treat any chart as a collection of salient data points. This is where the information in the chart is. And for like a bar chart, it's going to be the top of every bar and the location of every tick mark along the data axis. For a pie chart, it's going to be the location of the segments, the boundary between the segments. For a line chart, for a line graph, it's going to be a dense collection of points that make up that line. And you can treat, to a large degree, most charts as a point prediction problem. And our model, specifically, as I said, had to be very robust to spurious artifacts. So that means that we had to do a lot of data annotation to make sure that we train our model to ignore those spurious artifacts. And we got a very good performance on this problem. Previous efforts to do this kind of information extraction from charts have really not been very robust to artifacts, and in fact, they kind of ignored that problem altogether. They have been demonstrated on extremely simplistic charts, the kind that you would see, I don't know, on the web, the kind that you would see in a business PowerPoint. They're not the kind that you see in scientific charts, which are very dense because you have page limits and you have a lot of information to convey graphically. And so we needed to make sure that we kind of go a step above and cover those really hard, challenging problems. The model architecture is pretty straightforward, but it really came down to the data and the training. Now this is kind of what our results look like. Those red dots and blue dots are where the model thinks the data is in these charts. And that's half of the problem. Now you know where the data is. To get the data out, you need to know where the labels are. And the label part, the label recognition part, because it's text, is actually pretty easy, it's just OCR. But aligning the two is the next step. We have to make sure that we pay attention to the correct placement of the labels relative to the corresponding data points. We have what we think is a good solution for that problem, but that is still a work in progress. And then extensibility of this work is really important to us as well, because we want to make sure that this works not just for one class of problem or one class of data in this problem, that it works for general problems as well. And we've demonstrated that for various types of charts, for various chart elements, like extending to error bars, for example. We're very happy with those results so far. Now, if you're able to get all of this information out of documents, out of information resources at scale, what can you do with it? I already said that you can accelerate a lot of kind of mundane human efforts that you could throw at the machine learning model instead. But I think the real value here is in building knowledge graphs out of these resources and then using those knowledge graphs to see emergent phenomena that you wouldn't see unless you have the scale. And there's a lot of opportunities here. We know that natural language processing is a very powerful technique for interacting with information resources, so that's the obvious interface. And then visualization is going to be very important as well, because sometimes people want to explore your knowledge graph or explore your knowledge resource rather than ask or query about it. And then for some domains, you have ground truth. You know what the right answer is. You have databases that have been curated. So any machine-generated resource like this must necessarily have interfaces back to those reliable resources, and both for retrieving the correct answer when it's necessary, and also for feeding back in when you have confidence enough that you can contribute back to that knowledge repository. So that is the end of my talk, and I'm very open to questions now.
Questions?
When it comes to accessibility to screen readers, how is that changing how screen readers are actually made?
You said accessibility for screen readers?
Yeah, so like you're talking about like writing track visualization graphs and things like that. And a lot of times like now with accessibility, we're fixing like websites and things like that to be readable for screen readers. But
yes.
would it change how that screen readers
So screen reader support requires a lot of human intervention. The developer of a screen reader supported website must queue where the ordering information goes for a website that natively supports screen reader technology to its full potential. Otherwise, the browser or whatever interface tool has to guess at what the ordering needs to be, or the user has to interact with that content, like select, read me this content, read me this content, read me this content. And so you still have that problem of where the structure and where the ordering of data comes into play. So they're related, but it's not a solved problem.
One more.
Are you guys doing or planning to do any work in the area of retrieval augmented generation?
Yes.
Combining this work with that work?
So yes, retrieval augmented generation is very important, especially for generative machine learning, and we are heavily invested into that area of research. Especially since we work in the scientific domain, where you have reliable resources that you can leverage if you have a generative model that you want to exploit that information and produce something for the user. So absolutely yes.
Okay, thank you very much.
Thank you.
Thank you.